Welcome viewers to the 19th lecture of the course spur and helical gear cutting. So, last day when we were discussing, we were talking about the the hand of the helix and the relation between the circular pitch of gears to be cut and the pitch of the hob, etc. So, let us start right away with those discussions. We were discussing last time this one for cutting a 4 millimeter module straight tooth spur gear in gear hobbing machine. Normal pitch, I made a small correction here, it was written previously pitch. So, I have made a change. Normal pitch of the single start hob thread rounded to third place of decimal is in millimeters. There are 4 options given. What do we exactly mean? If you have a look at the sheet of paper, we have this sort of a relation existing. Say this is the basic gear, okay, and with this one we are drawing these being the gear teeth. We have the hob, which is actually a worm with cutting edges. This sort of a relation is existing, which means the circular pitch is equal to the linear pitch, but if you remember in the other view, the worm gear being like this being a spur gear, the teeth are of this type and the hob has to be at an angle so that on that side it matches with its thread matches in direction, in alignment with the teeth of the gear. So, basically this distance that we have shown as circular pitch, circumferentially this distance has to be equal to the distance between the threads, and that means the normal distance between the threads. Okay. So, if we look at the hob alone, it is this distance, not the axial distance. So, we are not talking of axial pitch, we are talking about the normal pitch. Normal pitch has to be equal to the circular pitch of the gear. This is the equality which has to be maintained so that they will be in mesh. This particular equality does not necessarily have to be satisfied in all cases, but it is the general case. Yes. Okay. So, we have the normal pitch equal to pi into module. How do we get that? Sorry, the circular pitch equal to pi into module. How do we get that? Let us take a fresh sheet of paper. Yeah. So, circumference being equal to pi into pitch diameter, this divided by the number of teeth z, okay, gives us pi into m, okay, pi into m. So, that means the circular pitch, okay, sorry, this being a spur gear, this is equal to simply the module and this is multiplied by pi. This is the distance that we are talking about. This is the distance we are talking about. These are the 2 teeth. Okay. This has to match with the normal pitch of the hob, and therefore, we have what is the module? 4 module, 4 multiplied by pi. This one will have to be equal to the normal pitch, and this is equal to 12.566 and some trailing numbers. So, we find if we come back to the question now, the options are 12.566 millimeters, 10.566, 14.566, none of these. Therefore, A 12.566 is the correct answer. Normal pitch of a single start hob thread. Okay. Once we have understood this one, let's move on to other questions. Linear pitch of a rack is 11 millimeters. Okay. So, let's draw a rack. It is in mesh with a pinion having 20 teeth. Outer diameter of the pinion is. So, this is the pinion. Etc. So, we need to find out what is the outer diameter of the pinion. Now, as they are meshing, therefore, linear pitch of the rack must be equal to the circular pitch of the gear. Circular pitch once again is pi into module. Okay, so, pi into module must be equal to 11 millimeters. Let us use this part, this is clear. So, we have 22 by 7 into module equal to 11. This and this they will cancel and module is equal to 7 by 2. Okay. Outside diameter will be equal to, okay, outside diameter will be equal to pi d p plus 2 module, pitch diameter plus 2 module. This is equal to pi m z plus 2 m, which means m being taken common. I'm sorry, please drop this one. Okay, I'm extremely sorry, drop this one. This is in the circumference, so it's not in the diameter. So, diameter plus 2 module, mz plus 2 module, m into z plus 2. Okay. So, once we are knowing the module, we write 7 by 2 into z plus 2 must be equal to 7 by 2 into what's the number of teeth? 20. So, 22 cancels out 11. So, answer must be 77 millimeters. Okay. So, coming back here, let us see, B is the correct answer, 77 millimeters. So, once we arrive at that, let us move on to the second question, third one, calculations without differential. Last day we had identified a problem that is the differential really necessary, and we had a theoretical discussion at the end of which we had reached the conclusion that if we have a machine without differential, there will be gear ratios which will be very difficult to implement. Okay. So, now we will follow this up with a numerical problem. That is, why is the differential becoming absolutely essential for the gear hobbing machine? Suppose in a particular hobbing operation, the number of teeth to be cut is 20 and the lead of the helix is 1000 millimeters. What should be the gear ratio UI if no differential is used? The feet in millimeters of hob vertical movement for every rotation of the workpiece is S is equal to 0.2 millimeters per revolution of the workpiece. So, what do we have? We have a helical gear being cut, its number of teeth is 20, the lead of the helix is 1000 and UI has to be found out, no differential is used and the feet in millimeters of hob vertical movement is 0.2 millimeters per revolution. So, what we say is that if we are cutting a spur gear of 20 teeth, then for every rotation of the workpiece, the hob rotates z by k times. Now, you might ask me, what's that? How do we get that? So, if we come to the piece of paper, we will have n worm gear divided by n worm is equal to n let's use gear blank divided by n hob equal to K by Z gear blank. This is accepted, K by Z. Okay. Now, if we are cutting a spur gear of Z number of teeth with K number of starts of the hob, in that case I can say that therefore n hob will definitely be equal to Z gear blank Z by K into n gear blank. So, if this is 1 for every rotation of the gear blank, NH will then definitely be equal to Z by K into 1. So, if I have to have one rotation of the gear blank, I have to rotate NH, that is now the hob rotation has to be equal to Z by K. This is understood for spur gears. We have done it so many times. But now the situation is changing. The situation is changing in this manner that in order to cut a helical gear, we are deciding that every rotation has to have an additional rotation of the blank, so that this cutting will not proceed this way, but the cutting will be proceeding say this way. And in that case we will be putting some extra rotation of the blank, and that will lead the cutting action, the downward motion, and it will be proceeding. Next point of cut will be here, next point of cut will be here, like that. What is this extra rotation? In the theoretical discussion that we had, we came to the conclusion that this extra rotation is related to the downward motion in this manner, this being equal to pi dp, this being equal to lead. If you move down by S, that means say 0.2 millimeters, if you move down point per rotation, 0.2 equal to S, then this much is the amount of rotation that is required to be added. So, with every rotation, with the downward movement taking place this way, the extra rotation is this much. I am moving down this, you maintain this extra rotation, so that at the end of the day I move down by L and the extra rotation is 1 rotation. So, mind you, this is extra rotation, this is already rotating to maintain n is equal to Z by K and workpiece rotation is equal to 1, that is already maintained. The extra rotation takes place this way. Per rotation that is taking place, I am moving down this much, you add this much. Okay. So, how much is this? So, from similar triangles we can easily find out this x amount of rotation must be equal to S by L. Okay. That is x by pi dp is equal to x by pi dp is equal to S by L. So, this must be x by pi dp is equal to S by L. So, that means this is the actual fraction of one rotation. This is a fraction. See, this is one full rotation, a part of it. So, the fractional amount of rotation is nothing but S by L. So, if this be so, therefore, now if we can make a statement, if hob rotates Z by K, workpiece rotates 1 plus S by L, that is it. This is the extra amount of rotation expressed in fractions of rotation, one full rotation, fraction of it. Hence, the gear ratio previously UI was equal to K by Z. Okay. UI was equal to, if you started from hob and you went through all the gearings and say all the other gears and belts and bevel gears, etc., they were 1:1, you would have had this to be K by Z, output by input. Now, there is an extra rotation added because the output is not 1, but 1 plus S by L. UI is equal to output rotation, which means gear blank rotation by Hobb rotation, and gear blank rotation is not 1 anymore, it is this thing 1 plus S by L. Okay. Previously, we were putting 1. So, in that case, let us take a practical example, this particular numerical problem. All these things we have already discussed. Okay. UI equal to 1 by 20, that means K by Z. K is single start worm and number of teeth to be cut is 20. Okay. This is 20. 1 plus S by L. Oh my God. So, 1000 comes in the denominator, so that we have this one to be equal to 1000.2 in the numerator and 1000 at the denominator. This 1000 gets multiplied by 20, 20,000. 1000.2 divided by 20,000. I cut it, I remove the decimal, so it becomes 10,002 divided by 2 lakhs, which is equal to 10,001. Wait a minute, have I made a mistake? Yeah, there is a small mistake here. Please look at this. We have finally 10,002 divided by 2 lakhs. I intend to cut it with 2. I am sorry, please make this correction. 5001 divided by 1 lakh. This is quite a difficult, fraction to attain. How do we attain this fraction by gear ratio? Now, first of all, we will try to divide it into products if they allow, and after a lot of permutation combination, the gear ratio will be difficult to obtain. Instead of that, if you employ the differential system, that means there will be lead change gears and the differential, the problem of achieving a particular number of teeth and problem of achieving a particular helix angle, they become totally different. Okay, they become they don't remain an integrated problem, but they become totally different from each other. They become mutually exclusive. So, this is the reason, to avoid such difficult gear ratios, we go for finally the differential instead of a no differential system. Next, the Willich equation or the Willich equation, whatever be the pronunciation, I am not very sure. The 4 bevel differential. What did we do when we came across this particular mechanism? We said that this is going to we divided it up into 2 different cases, where we said that if this is written slightly upside down, Ni input, I am giving the input here, I am giving the second say input through the arm rotation, and I am getting an output here. I can also give this one as a second input, this one as the first input, and get the arm rotation as an output. This is what we had done in the actual numerical problem on gear hobbing that we had discussed. Now, what are we trying to do? We are saying that at that time we had roughly estimated the rotation of the arm, by a thumb rule method. We can use the Willich equation in order to actually calculate what will be the arm rotation if one of them is held steady. Suppose this Ni is equal to 0 and No is equal to some particular value. The arm rotation in our numerical problem was the output. So, the Willich equation says that the output rotation with respect to the arm rotation divided by the input rotation with respect to the arm rotation will bear a constant ratio, which is obtained by keeping the arm steady and rotating the system. So, if I rotate Ni looking from this particular direction, suppose it is rotating clockwise and this is rotating counterclockwise. Let us draw a figure and show it. Okay. Suppose this is gear 1, this is gear 2 and this is gear 3. So, if it is rotating say this way, if it is rotating this way, this will rotate this way. So, that if I look from this direction, I will find that these two are having different directions of rotation, different sense of rotation. So, coming back to this problem, E is defined to be, if the arm is kept steady, they will simply have the same rate of rotation, but the sense will be opposite. So, that E will be equal to -1 for this particular 4 bevel differential, where the bevel gears are all of the same number of teeth. Okay. So, E is equal to -1. So, if E is equal to -1, okay, and if we keep one of the bevel gears to be fixed, so I put NO is equal to 0 for example. So, I am giving an input Ni, I am keeping NO to be 0 and I am trying to find out the arm rotation, and you will find it will be minus Na divided by Ni minus Na equal to -1. Therefore, if you solve it, it will become, let us solve it quickly, NO minus Na divided by Ni minus Na equal to E equal to -1. NO we put to be equal to 0, and therefore, we have minus Na divided by Ni minus Na equal to -1. If you cross multiply, you will get Na. First of all, we remove this negative sign. Na is equal to Ni minus Na. Therefore, we get twice Na is equal to Ni. Therefore, Na is equal to Ni by 2. That is what we had taken up at that time, and by applying Willich's equation, we can actually calculate it out to be this much. So, this is the bevel differential, and this is what is used there. And when you have two different rotations given, suppose NO is not 0, in that case what will be the arm rotation as a result? It will be simply equal to Ni plus NO by 2. So, it will be basically, as we had stressed at that time, an algebraic addition of the inputs divided by a particular factor. As we have understood here, the factor is 2. That means, just a moment, excuse me, Na is equal to Ni by 2. I have written it wrongly here, please correct. In the calculations that we have done, it has been done correctly. When I distribute this PPT in PDF form, I will make this correction. Extremely sorry. Okay. So, we understand that arm will be always equal to half of this input, and in the same manner arm will be equal to half of this input if this is put on and this is put off, and both of them, when they are acting, it will be the algebraic addition of the halves of these two input RPMs. Okay. So, as we had claimed, this does a sort of addition, this bevel differential. Okay. We will take a short break from here to have a look at how this actually operates. So, let us see. This is the arm, and that is one of the bevel gears at the top. This is put off, and the bottom one is rotating. Okay. Once again, let us see. Yeah, it is rotating. See the arm, this is rotating, and the bottom one is not rotating with it, but it is having a separate RPM. unfortunately I could only get hold of this particular differential where the bevel teeth, they are not the same. That means the bevel gear diameters are not the same, but anyway, something is better than nothing. Okay, so this is what we had considered in our setup. Coming back, let's start again. So this one is now understood and accepted. Now comes, we had a discussion on the hand of the helix. How do we decide upon the hand of a helical member? The basic procedure is, hold a machine element, it might be a screw, a worm, a hob, a helical gear, away from you. That means this particular arrow is designating that you are here, and you are holding this away from you. It's going away from you. Okay. If it's a right-handed helix, it twists clockwise, okay, while moving away from you. Okay, so this is moving away from you, but in which direction is it twisting? Obviously, it's twisting counterclockwise, so this cannot be a right-handed helix. What about this one? This one is rotating this way clockwise while moving away from you, so this must be right-handed. So the left side one is left-handed and the right side one is right-handed, and they cannot be mutually changeable. If you put it the other way around, it does not become right-handed. No. So this one is right hand, this one is left hand helix. Let's take a problem. I hope you can read it. The helix angle of a hop cutter, a right-handed helix, is 5 degrees. It is used for cutting straight tooth spur gear. Axis of the hop cutter should be as in figure 1, as in figure 2, and as in figure 3. Which one is correct, or none of these? So let's look at these. This one, the axis of the hob is crossed with the axis of the blank, that means at 90 degrees. But this won't do, because the thread of the hob has to align itself in the direction of the teeth being cut. Here they will be at an angle. Here the thread appears to be aligned with the teeth of the gear, but the problem is these are the threads that you can see, so they are away from the gear. The other side of the thread, which is facing the gear teeth, that is not aligned with the gear teeth. Why? Because it's moving this way, it's crossed, it is not vertical. So this is also not correct. This one is correct, because here this is the part of the thread which is not visible to us, but it is definitely in line with the teeth, where it is meeting the teeth, okay, in contact with the teeth, and hence the answer is as in figure 3, as in figure 3. Now coming to this, how do we decide? This problem also we had identified. How do we decide whether a particular hob is correctly aligned with the workpiece or gear blank? For that, let's see. We are taking the case of a spur gear with straight teeth, and this is a right-handed helix. So the dotted one is the one which is touching or on the side of the gear teeth, in contact with the gear teeth. The basic rule is that these dotted threads, okay, traces of the thread which is in contact with the teeth, after proper proper positioning or orienting of the hob, these dotted lines should align themselves with the potential teeth, okay, the teeth which are going to be cut. They have to get aligned. I mean, the thread has to get aligned. The dotted thread has to be aligned with those teeth. So here obviously the dotted thread should be vertical. Now let's try this out. Is this direction correct? No, not at all. It is becoming more and more horizontal, the threads, the dotted threads. So this is not allowed. Second case, let's try it out. The blue one is the gear to be cut, and these white vertical lines, they are the traces of the teeth. Now, let's give it a rotation and see what happens. Yes, this seems to be it. Therefore, the dotted lines are matching with the direction of the teeth being cut, and therefore we say that for cutting a spur gear with right hand hob, the rotation angle is simply the helix angle of the worm. Okay. Second case, there can be so many combinations. I am having a right-handed right-handed hob, and I want to cut a left-handed helical gear. So this is the axis of the hob. Hob is rotating about this axis, and what are these threads? They seem to be different. Yes, to add to the variety, I have incorporated a hob with 2 starts. Can you see there are 2 starts? It hardly makes a difference. You can definitely use a 2-start hob. There's nothing wrong with that, and in fact you will be more confident after going through that sort of a problem. So is this right-handed hob? Yes, it's moving away from you as it rotates clockwise. The dotted part is on the other side of the hob. What about the gear? If you are here, as it moves away from you, it rotates counterclockwise. So this must be a left-handed helical gear, and the axis of rotation, which has not been drawn, it is in this direction. Okay. So how do I rotate it? The golden rule once again is that get those dotted lines aligned with the direction of the teeth. Yeah. So this is the correct rotation. So you have to give quite a large amount of rotation here, which happens to be equal to, as written above, angle of the hob, helix angle of the hob plus helix angle of the gear. Please remember, helix angle of gears, they are expressed with respect to the slant of the teeth with the axis of the gear. So this is for right-handed hob with left-handed helical gear. Okay, another combination, right-handed hob with right-handed helical gear. Here the teeth appear to be almost aligned, and if their helix angles are equal, they will be perfectly aligned, but that might not be the case. The helix angle of the hob might be 2 to 3 degrees or something like that, while the helix angle of the gear might well be different. So the angular rotation ultimately is the difference in these helix angles. See the slight amount of rotation which is required to make these teeth exactly get aligned with the gear teeth. That's it. So it's a difference which has to be the amount of rotation. Taking another case, what's that? Left-handed hob. How do I know it's a left-handed hob? While it's rotating and moving away from you, it's rotating essentially in a clockwise direction. Okay, that's good. And what about this particular thread? That's a right hand thread, because while moving away from you, it has to have rotation in a clockwise manner when you are looking at it from this side. That's good. So how much is the rotation? Let's try this out. Yeah. So once again, quite a bit of rotation is required, and this comes out to be the helix angle of the hob plus helix angle of the gear. Okay. So let's end up with a couple of multiple choice questions. In the gear hobbing process, the hob shape is similar to a spur gear with cutting edges? No. A reciprocating rack with cutting edges? Not exactly. A worm with cutting edges? Yes. And of course, none of the others in that case is not applicable. So in this case, the correct answer is a worm with cutting edges. In gear hobbing, indexing gear ratio UI depends on number of teeth on the gear blank, module of the hob cutter, and RPM of the hob cutter. Let's see, what is it dependent upon? Let's write down here. We know that starting from the hob rotation, suppose how much? Rotation of hob multiplied by UI must be equal to, we are considering that there are no other machine elements in between, no gears, no belts, no bevels, no worm and worm gear, etc. Hob UI, we must be getting gear blank. Okay. Therefore, UI must be equal to rotation of gear blank divided by rotation of hob, and this we know has to be equal to K by Z. Okay. So, now we understand that UI is equal to this one. It's a constant, K by Z. So, now if I say that it depends upon the number of rotations of the hob, I can definitely say no, it does not. You change the rotations of the hob, NGB will also change, so that this will be untouched. If you double NH, do you mean to say that K by Z will change? No. So, it does not depend upon the number of rotations of the hob. Does it depend upon Z? Yes. If you are cutting a different number of teeth, you will find that UI will change. So, let us come back to the problem. Does it depend upon the number of teeth on the gear blank? Yes. Module of the hob cutter? Well, K by Z did not contain module of hob cutter. RPM of the hob cutter, just now we showed that RPM of the hob cutter is not going to affect it. It is only equal to K by Z. Therefore, the correct answer is number of teeth on the gear blank. So, with this, we come to the end of the 19th lecture. We have one more lecture left, and we will pick up our loose ends in that one. Thank you very much.